Okay, so let's gradually start. So welcome to the fourth week and third lecture of the fourth week. Today we are going to finish whatever we have not finished yet on the Wednesday's lecture. And we also go through some consolidation exercises. So today is, I believe, August 16th already. What happened on this day in history? In first year BC, when man consolidated his power in China and was declared Marshal of State. In 1328, the House of Gonzaga seized power in the Duchy of Mantua, and they would rule until 1708, almost 400 years. So who can guess where this might be happening, where this House of Gonzaga actually were located? Does anyone have any guess? Where they ruled for 4 centuries. Almost like in the Game of Thrones. So this was, I believe, the northern part of Italy. So next, so in 1858, US President James Buchanan inaugurated the new transatlantic telegraph cable by exchanging greetings with Queen Victoria of the UK. In 1913, Tohoku Imperial University of Japan, modern-day Tohoku University, became the first university in Japan to admit female students. In 1930, the first color sound cartoon, Fiddlesticks, was released. In 1989, a solar particle event affected computers at the Toronto Stock Exchange, forcing a halt to trading. Okay, so we will continue on mutability, namespaces, and functions now, and then we'll play a little bit with some text processing. So last lecture we discussed the scope and the namespaces, right? So a namespace is sort of like a mapping, a dictionary from names to objects. And when Python starts, when you start this Python interpreter, so you are by default in the global namespace or global scope. And whenever you call a function, everything within a function is in its local scope, the local visibility. So, and when you have a variable in the function, so of course you only first consider all the variables inside of the function, and then on the next priority you go outside of that function to the next level. So you kind of look outer. So in this example, we discussed which variables are global and which ones are local, or which objects are global and which are local. Who can tell me which ones are global ones? Global? Local, yes, this is local. And X is also local. It's defined within the function. And A is the global one, B is the global one, and also the function itself is defined in the global scope. What happens here? So what will be the result of this function call? Who can remind me what will be happening? So we have this variable I, one variable I which is defined in the global scope, and the other variable also called I which is defined in the local scope. And then we call this function for this value of 10, right? So we pass it inside of the function, so x becomes 10. So what will be the result of this call? Yes?
11.
Yeah, 11. So why? Because we start by looking at the local scope first. So we look at what is this I, and we see that it's defined inside of the function, so we return 11. So if we omit this line, so we will use this, the global one. This is our next priority. So now who can tell me whether this code will work or not? So you see that we can define some functions within the functions, inside of the functions. For instance, you might define some auxiliary function inside of a more general function. So who can tell me whether any of these calls, F for 10 and G for 10, will work? Will they both work? None will work? One of them will work? What do you think?
I think the second one, G10, will work.
Yeah, exactly. So it will not work because it's only defined within the local scope of the function f. As soon as we leave function f, so we actually remove, we delete the memory of these local variables and objects. So let me exemplify it here. So here is just the same code. So visualize execution. Why I cannot visualize it? Okay, I probably have to refresh this page again. Okay, so you see that it gives us an error saying like this, G is not defined. It's not defined globally, it's only defined locally. Again, as soon as we leave function f, G no longer exists for us. So now let's go and remove this part. Let's just run the first part. What will be the resulting value? So we pass this value of 10 inside of the function f, so x is now 10. We go through this function, so we see the definition of the function g, and then we go to the next, so I is assigned to 2 in the local scope of f, and then we call g for x plus I, so we go inside of g. So what will be the resulting value? So let's go and visualize this. So we define the global I, so we see that it's defined in the global frame. Then we also define this function f in the global frame. We go and call the function for the value of x. X is defined as a local variable of that function, so we pass the value 10. Then we define function g in the local scope as well. Then I, so you see that this is the second variable called I now, defined in the local scope of the function f. And then we pass and call this g for this x plus I. So we have this x as 10 and I is 2. So we pass it inside of g. And we go inside of g. Now we have the third variable I, which is 1. And we return x plus I, which is 12 plus 1. So the resulting value will be 13. Okay, is it clear what's happening here? Okay. Okay, so, oops. So the next one, do you think this code will work? So now the change is that we remove, what do we remove? We remove this I assigned to 3, and we remove inside of the G, and we have this I here. Let's assign it to 1. So will this call work? Who thinks that it will work? Who thinks it will not? Okay, so let's go and try. So we have this I, which is only defined within this function f. But we also use I over here, right? So we again go through this definition of the f in the global frame. We call this function f for the value of 10. So we pass the 10. We define the function g inside of f. We go and define I inside of the f. And then we pass this 10 plus I, which is 10 plus 1, inside of the function g. So now we go inside of the function g. X is now 11, right? And we return the value of x plus I. So I is not defined in G, but it's defined outside. So we go and search for this outer space. And we see that it's defined as 1, so the return value will be 12. It still works. Okay? So we can look outside, but we cannot look inside, right? So as soon as we leave the function, we lose the memory about its own objects. Okay. But of course, please do not do like this. So it's not really readable. If someone else will be reading your code, it will be very confusing. So you need to make sure your code is readable and comprehensible by these other people. And in order to make their life easier, you would probably define all these local variables in more meaningful way, right? You have like this meaningful names of the variables. So instead of I, you would have either F, either G, and it will be much easier to understand for the other people who will read your code. So another aspect of functions is related to their return function. So who can tell me what might be the issue with this code? So here's the code, the function that takes a list of marks as integers. And then if at least one mark is less than 50, so we need to say that the student might fail the subject. Yes?
It just iterates through the whole list.
Yeah, exactly. So so it's syntactically correct, but it's not really efficient, right? So the function should just return true if any mark is below 50. So as soon as we see the very first mark, which is below 50, we need to actually exit. We are done, right? Here we loop through the whole list, right? We iterate through the whole list. Even if the first mark is already satisfying this condition, we still go through the whole list. So how we modify this code to make it more efficient? What do we need to do? Yes? Sorry? Yeah, it's one of the solutions. You can use break. The other solution is just use the return, right? So as soon as you see that the mark is below than 50, you can already return that it's true. The student is about to fail the subject. Otherwise, if no mark is below 50, you just reach this point and you return false, right? Okay, is it clear? So again, the code is syntactically correct, but it's much less efficient, this one, okay? You also need to think about the efficiency of your code. The next one. So when we talk about functions, we typically talk about parameters and arguments. Who already know the difference? In mathematics, we typically use the term arguments. But in programming, we have parameters and we have arguments. What's the difference? Who can guess? So there are two scenarios of using the function. You define the function, and then you call the function, right? So when you define the function, in the function definition, you use these parameters. So the names that appear in this definition. And arguments are those like particular values that you pass inside of the function when you call it, okay? That's the difference. So here, what are the parameters? So here's the function count positive, or count pos. So it counts the number of positive elements in the tuple. So you see that this is our parameter, top. And those particular values for the tuple, they are called arguments of the functions. So whenever we call the function, we pass arguments to that function. Whenever we define the function, we define it with these parameters. So this is called parameters if it's in the function definition. When a particular value is passed inside of the function, it's called argument. Okay? Is it clear? Great. So another thing that we already mentioned, that for some of these parameters, we can set up some default values, right? So for instance, if we want to count seconds in years, so typically in the year there are 365 days, we can set this default value for this parameter as 365. But now there is some problem that is related to mutable data type. So let's start with this example here. So suppose we, for now we have immutable data type, it's just integer. So we assigned this number of days to 365. This is our constant we specify that this is a constant by using uppercase. It's still like for Python, it's a variable, it's just for readability. For someone else who reads your code, if it's uppercase, they assume that this is sort of something that will not change. So you say, okay, it's some constant number. But again, for Python, it's not constant, it's just variable. You can change it. So, and you say, okay, the number of days is assigned to that value. And then your function returns days times 24 times 60 and times 60. So, and then we print this, the function, the result of the function for the default parameter, 365. So, and then suppose we decided to update this. Do you think the result will change? So first, we do not pass the exact number of days, meaning that we'll use the default value of that parameter. Then suppose we decided to update this particular variable. Will it affect the result of this, the second call? Will the result be different or not? So let me just visualize this. So we define this num days in year. Then we define the function. You see that we have this default, it's called arguments, but okay, so it's default value, right, for our parameter, 365. And seconds in year is pointing to that part. And now we print the call for this default value, 365. And we return some result. So we return, and we print the returned value. Now we update this variable, num days in year. We say, okay, it's now 100. And you see, we updated the variable, but the default parameter is still the same. It was just assigned once. Okay? It's still pointing to the same place, and when we call for the second time, we see that the result is exactly the same. It's not affecting. Okay? So these default arguments, they are set only once when you define the function. But, so our default value was integer, immutable data type. So what happens when we have mutable data type? For instance, instead of integer, we have a list. And then we modify this list. So what will happen here? So here is another example of adding an element to a list. So we have some value, and then we also have this list. And the default value for the list is empty list. And then we take this LST and append this value and return this list. So what will happen if we now call this function for the default value? So we only pass the value, but the second one for the list is the default one, so it's empty list. So what will happen here? Will we have just list of 1, list of 2, list of 3, or list 1, 1, 2, 1, 2, 3? So let's again visualize this execution. So we go through this function definition. So this is our, again, default argument. It's pointing to this empty list. So, and now we pass this value of 1 here, and our LST is pointing to the same place, right? So LST pointing also to this empty list, and then we add the value there. And you see that this is a single object, and now we modify, so we modify this default one as well. So we return this list 1, okay? Then we go to the next one. Again, the default value is that this is empty list. But here you see that we modifying the same object. It's no longer empty list. We already have elements there. And you see that if we use this mutable data type as the default argument, we are actually modifying this. So if you want to make sure that you always start with an empty list, you then need to pass it explicitly like that. So in this case, you'll have just 3 lists of single element, 1, 2, 3. Okay? And the other way around is that you assign this to none, and every time you check whether it's a non-object. So let me just illustrate this. So instead of empty list, we assign it to this non-object. And then we check if LST is none. We assign, sorry, it's L here. Okay, let's just use LST. So, and we say LST assigned to the empty list. And then we again append. And now we can again remove this second parameter and call this for this 1, 2, 3, only passing the first value. So here the result is the same as in the previous call, just the second way around. Okay? Who can tell me whether this particular call will work if we swap the order of our default and non-default parameters? Suppose I decided to put this as a first. Can I do that? What do you think? So can I swap this order of this value and LST? So LST has some default value, and the value itself doesn't have the value, I mean the parameter called value. Can I swap the order? Yeah, we cannot swap the order because first we need to provide the parameters for which we do not have the default value. And the default one, they should go after them. So I will get an error here. So the error will explicitly say that the non-default arguments follow the default arguments. Okay? So in this case, what do you think will be returned? Let me just increase this font. So in this case, there's a function f. So it takes a. So it doesn't have any default value. Then C and D, C has 3 and D has 4 as a default value. And then we print these values and we return the non-object. Suppose we call this a function for these values of 1 and 2. What will be printed? Will it work or not? And if it works, what will be the result? What do you think? Will it work? Who thinks it will work? So we have here 3 parameters. We pass only 2 values. But for these 2 parameters, we have the default one. So basically, the answer is that it will work. So A will be assigned to 1. So it's sort of like 1-to-1 match. So A, it doesn't have any default value. It will be assigned to 1. C will be assigned this value of 2, and D is not provided, so it will just take its default value. So we'll have 1, 2, and 4. You can also specify explicitly which of the parameters is assigned which value. So for instance, you would like to say that for C, you need to use the default value, but for D, you would like to provide some non-default one. So you can explicitly do this assignment. You can just provide explicitly that D is assigned to 2. And then in this scenario, so A will be assigned to 1, C will take the value of 3, the default one, and D will be assigned to 2, okay? Now there's a question for you. So you can probably take 2-3 minutes to discuss in the groups. You can just chat with your peers. So which of these calls will work and which will not? Okay, so we have, again, the same function definition. So it's A doesn't have any default value. C and D, they have the default values. And then we have the first call, the second call, third call, fourth call, and the fifth one. So take 2-3 minutes. You can discuss with your peers which ones will work. And for now, I'll just copy this in Python tutor to illustrate. Okay, so let's start going one by one. So will the first call work? You sure? So what it will return to you then? But you see that we here, like we asking, okay, evaluate what is A, right? We need to provide some value for the A. But we did not do anything. We did not provide. So here we require that A needs to be assigned some value. Like we need to pass at least one value, right? So the answer here is that this particular call will not work because we have at least one parameter which is not assigned any default value. So what about the second one? A assigned to 1, and then 7. Will it work? So what it should return us? 174. Okay, so let's keep it in mind. The next one, will it work? The next. Exactly, so it will not work, and now the question is why? Yeah, so we'll have this sort of like positional matching. So A will be assigned to 1, but at the same time, we also see that A is assigned to 2. It's ambiguous. It's not clear what do you mean by this construction. Now, the next one. So why it will not work?
Because the variable b isn't defined in the function.
Yeah, so we have this, we provided b, which is not defined even in the function. So, and the next one? Who thinks it will work? How many of you? And who thinks it will not? Okay, most on the optimistic side. So now let's go one by one and see the reasons it will work and it will not work. So I'll just try to execute and we'll fail like line by line. Okay, the first one, so I say, okay, so the first one, what was this happening here? So this one should not work. So let me just, yeah, it basically just gives us this syntax error already. So we will discuss the types of errors, but whenever we run the program, first the syntactic correctness is checked. So, and then we only go to this runtime errors, like the errors that happening when we run actually the program. So here we already have an error saying syntax error, positional argument follows keyword argument. Okay, so it will give us an error exactly because of that. So let's comment this out. And now let's again try to run it. So we are running the rest of the code. And you see the very first one will also fail because it says like we are missing at least one required positional argument. Positional means it will be assigned by the position. So, and let's go and comment this out. So this one will not work because we require at least to provide the value for A. The next one. So the next one, you see, it's exactly this ambiguity error saying we have like A assigned to 1 and 2. Okay? So this will not work either. Then we go to the next one. So it says, like, I got this unexpected argument b. I didn't expect that. You didn't say anything about b here in the function definition. So it doesn't work either. And finally, the final one. And the final one works. Why it works? Because even though we did not match it by the position, we matched by the name. So we provided the values for A, for C, and for D. When we provide this explicitly, we do not have to follow the order. Okay, the order might be any. Okay, so let's go to the next one. So what we need to discuss. Okay, we arrived to the class exercises and the consolidation part. Okay, so let's play this ciphering game. So we have a string which is encoded somehow, ciphered. So there is some code. So who can try to guess what the original string is? Any guesses? Is it in English at least? Do you think it's in English? You can try to guess by the length of the words. So the length of the words roughly corresponds to the average length of English words, right? And this hint that this might be a, so you can assume that x is a, so there are multiple words that contain a in the middle. Now let's try to guess this one. What is the first string? Yeah, the first one is 10001, and this next one? Yeah, it's foundations of computing. So it's very simple cipher, which is called the scissor cipher. So it's sort of like a form of substitution cipher where you replace each letter of the alphabet with another letter by shifting the whole alphabet by a certain number of positions. So here you can shift it by 3. So in this particular example, I just shifted by 3 positions. So I took this x, y, z and put this in the front. So A will correspond to x, B will correspond to y, C will correspond to z, D will correspond to A, and etc. So now the task is for you to write a function called cipher that takes 2 arguments. So the first one is just the string. The second one is this shift, the number of positions. So it's non-zero positive integer called shift. So, and the function applies this scissor cipher algorithm to the with the corresponding shift to the provided string and returns the ciphered string. So if we provide foundations of computing, so we should get this as a returned value. So, and the input string, you can assume that it only contains uppercase English characters. Okay? So I'll give you 2-3 minutes to discuss how to approach this task, and then we'll go through the code. So you need to define the function called cipher. It takes 2 arguments. Okay? And it should return the ciphered string. And you can assume that all English characters are uppercase. And the rest of the characters should be preserved. If it's not an English character, non-alphabetic character, it should be just preserved as it is, for simplicity. Okay, has anyone finished? So let's go through this, one of the solutions. So this is our alphabet, just uppercase English characters. So this is our function definition. So we provide some string, we call it word, and the shift, the number of positions we need to move. So, and this is our resulting string. So we initialize it to empty string. And then we need to create this modified alphabet, right, with this shift. So how we create this alphabet? So we need to take this number of characters from the end and move them to the prefix. So we take this initial number of characters, the ending number of characters, so the suffix of that alphabet, right? And put them in the front of our new alphabet. And then take the rest of these characters from the initial alphabet. This will give us this ciphered code. So now we need to go through this initial string that we want to cipher, character by character, right? And if it's in our alphabet, right, if it's alphabetical character, we retrieve the position of that character in the initial alphabet. So we retrieve at which position it's in the initial alphabet, and then we take from the modified alphabet the character at the corresponding position. Okay? So we go, for instance, this F, we find its position over here, and then we take this character from the modified modified alphabet from the corresponding position. Okay? And we attach it to our resulting string. So, and let me just try to run this code. So let me increase the font here. So. Code. Okay, so I'm in the right folder now, and we call this cipher_py. So this is the encoded string. So again, the logic here is that this is our initial alphabet, this is our modified alphabet. So every time we go through the string, so we go character by character. For each character, we retrieve a position in the initial alphabet, right? And then we substitute, in order to substitute this character with the modified alphabet character, we just retrieve this character from the modified alphabet at the same position, right? So instead of A, we'll have X. Instead of B, we'll have Y. Instead of C, we'll have Z. Okay? So try to go through this exercise at home. I also provided the solution. It should be attached to the lecture slides. Now let's go to the second exercise. So the second exercise is far more related to the area that I'm working in. So, and I mentioned at the first lecture this Yoda of Silicon Valley, Donald Knuth, who published this magnum opus of like 3 books on the art of computer programming. So, but he was also like a very fun guy. Why was he? He's still alive. So, and he published this paper. It's a joke paper on the complexity of songs. So, and the idea here is that songs, the hypothesis, he stated the hypothesis that songs are becoming more and more repetitive, right? So, and most songs, they have some refrains, right? The refrains, they are repeated over and over again, and there are some verses that are not repeated. So, and he wanted to relate and get the most repetitive songs. So his idea was, where is the slide? Oh, sorry, where is the paper? Okay, so this is the paper. So this is how he formalized this idea. So there were like verses and the refrains, right? So if a song might contain M verses and it also contains this M refrains, And the complexity of the song is sort of like the number of these unique verses and unique refrains, right? So if you have your song only contains refrains, it's not that complex. It has lots of repetitions. It's very simple to memorize. So, and he studied several songs, and he tried to formalize them in terms of these verses and refrains. So the first song was Old MacDonald Had a Farm. So the extreme scenario would be, first, you need to, the song only contains unique strings, unique verses, and you have to memorize the whole song, right? The other extreme scenario is just full repetition of the same thing over and over again throughout the whole song, right? So, and he looked at the most repetitive songs, such as Old MacDonald Had a Farm, right? It's very repetitive because you just kind of have the same start, the same middle, the same end. You only change this type of animal and the sounds they produce. So the Old MacDonald Had a Farm, E-I-E-I-O. This is the song. So, and he then looked at also the other repetitive songs, so which is about the bottles. So the song is That Many Bottles Hang on the Wall. And guess which one is the most repetitive? It's contemporary song. So it literally has exactly same string repeated over and over again throughout the whole song. So let me scroll down here. And this is the answer. So this is the simplest song ever he found. It's called "That's the Way You Like." You like it, right? It's like, that's the way. You like it, right? That's the song. Who knows this song? It's basically just repeats the same string over and over again. It's nothing else, no other content at all. And this is the simplest song. So now we will try to evaluate the complexity of songs in terms of how repeated they are, how many unique fragments they contain. Of course, you can approach this in many different ways. We'll simplify our approach a little bit. So we'll look at how rich the lexicon is and how many times you repeat the same word over and over again. So, and for that, we'll use this useful concept. It comes from information theory. It's called entropy. So entropy is related to information. It's also related to surprisal. So here what you see is the probability of the event multiplied by the logarithm of that probability. So think about this as sort of like you have a coin. You toss a coin. You have two events possible, right? Whether it's heads or tail, right? So it's 0 or 1. So, and the amount of information, it's 1 bit because it's 0 or 1, right? You can encode it in 1 bit of information, the simplest scenario. But if it's a fair coin, you don't know actually whether it will be head or tails. It's 50-50 chance. So it means it has the highest entropy. So the entropy relates to the surprisal, how much you can predict the outcome, what comes next. So for instance, if we have unfair coin, so it only has heads, and we are guaranteed to have heads, our entropy and surprisal will be 0. Similarly, if we have a string A, and we are asking what will be the next character, and we only have the alphabet of A, so it will be just A. So it's 0 entropy. If we have two options, A and B, right? And every time we have 50% of A, 50% chance of B. So the entropy will be 1. So how we formalize that? So let me put it here. So we have two events, right? So each event has this probability 1 over 2, right? So, and how we evaluate the entropy in this case, so we take the first, say like we are evaluating the entropy of tossing a coin, right? So there are two events. Each event is 50% chance. So we take this probability of the first, the heads. It's 1 over 2 times logarithm, say the base is 2 of 1 over 2. So this is heads, and said this is tails. And then we have, again, log over 102. So, and we have here, we have 0.5 times minus 1, right? And the second one, so if it's logarithm with the base 2, right? So this one will give us minus 1, so we multiply it by 0.5, we get minus 0.5, and 2 times, and we get 1. So we have this negative to make this positive number. So the entropy of 1 is the highest in the case we have 2 outcomes, right? When we toss the coin, so we get entropy of 1, which means we cannot predict what comes next, right? We cannot predict whether it's heads or tails. So, and this is something, this is the idea that also is underlying the whole approach in the contemporary language models. And I will be talking about this idea, how it's incorporated in training language models the next week, next Friday. So I'll introduce you to language models, large language models, etc. But for now, let's just assume we have this notion of entropy, and it correlates with the surprisal or unpredictability of our outcome. And it basically says how complex our events are, event space is. So, and now what we'll do, we will try to measure the entropy of the lyrics of the popular bands. So we take all their texts. For instance, we take text of like hip-hop bands like Eminem, etc. And we compare them to this something like Rihanna. And then we see which one has the highest entropy. So the highest entropy means the lower compression rate. So there are many unique parts that you cannot actually compress together. So if it's all repeated parts like A, you can just say 10 times A, for instance, right? The compression rate will be high. If our lyrics contain many, many different unique words, the compression rate will be very low. So the higher the entropy, the lower the compression rate of that text. So let me now just go through this example because we don't have much time left and just illustrate how we evaluate this entropy. We will reuse the function that we wrote last week. Where is my, okay, so this is my notepad. So we have these functions that we discussed last week. So lyric set and lyric dig. So now we modified this lyric dig slightly. So this function takes this file name with the lyrics of that particular singer. We extract a bit longer fragment, just kind of make it more interesting. Then we, again, we identify the words and we clean these words, the punctuation, we just kind of try to normalize this. So we clean the punctuation, we lowercase this, and then we also added this extra part. So for instance, we would like to remove all these like function words because people tend to use the same function words because they need to connect the words like these prepositions, they also use pronouns, etc. So we can also have an option of removing them. But this part is still the same as we had before, so we just create the lexicon. So for each word, we count how many times we saw that word in this particular file, right? In this lyrics of that particular band. So, and we print the lexicon size, so the number of unique words in the lexicon, right? And we return this dictionary. So the dictionary will contain the word, and how many times the person used that word. So, and from that, we will derive the probability. So our entropy will now have this probability of each unique word. So we'll take the frequency normalized by the total number of words in that particular file, and it will give us probability. So instead of this like 2 events, such as toys in a coin, we have this like the space of the vocabulary of that particular singer. So, and then we go to entropy. Here in this file, so we have this new novel construction for you that we'll be discussing probably next week. So it says that take this file from lyrics, take all the functions and everything from this lyrics, and import it inside of that particular module in this namespace. So from lyrics, import the asterisk means we import everything from lyrics into that particular namespace. And because we use logarithms, we also use this standard library from Python, which is called math, to use this particular function of logarithm. And in order to get the entropy, we provide this dictionary with our frequencies, and we just normalize by the total number of words in the file, right? So this is sort of like how we get the probabilities, right? For each word, the probability of each word is the number of times we saw that word normalized by the total number of words in that file. And this is essentially what we have here. So we provide this probability times logarithm, and we provide the basis for the logarithm. Let's make it 2 for simplicity. And we make this number positive. That's why we had this extra minus here, because it will be negative. So, and let's start with the most sophisticated writer, Shakespeare. So Shakespeare will be our upper bound. So we take the file of Shakespeare. So here's the Shakespeare. And we read the file, and we will see how many unique words and the entropy of that of the text of Shakespeare. So what do I have? I have entropy.py. So here's the lexicon size of Shakespeare. So this is our sort of like upper bound. So, and we have the entropy. Now let's replace Shakespeare. What else do I have here? Let me check in this code. Let me go to this folder. And so I have, say, Rihanna. So we replace this with the file Rihanna. And we now run the same thing for Rihanna. So this is the lexicon size of Rihanna for the same amount of text. So we just guarantee that we're comparing the same amount of text. So this is our Rihanna. And you see that entropy is much lower. So it means we can compress it more effectively. So now the next one, for instance, we have the Beatles. How it's called? Okay, so let's take Stones, actually. Let's take Stones. So it's Rolling Stones. Stones. And we run this again. So this is our Rolling Stones. It's even smaller than Rihanna. So it's much simpler. So now the next one, whom do we need? Let's take Eminem. So Eminem. And for Eminem, you see that the lexicon size is comparatively large, like it's almost like Shakespeare, surprisingly. And the entropy is also very similar. It's much closer to this kind of Shakespeare level. So, and you can play with this. You can just download the lyrics of the bands. But there is one thing that I also wanted to mention because we are about to finish. So you can, this is a nice website that compares this complexity of this modern singers and bands in terms of the compression rate. How much you can compress. Again, if all your songs are very, very repetitive, the compression rate will be very high, right? So, and they compared, where they have, the most repetitive songs. You can actually look at the most repetitive songs. And they also created this chart of the compression rate of the singers. So this is the most compressed, the singers whose lyrics is the most repetitive. And this simple, it's mostly pop music, like Britney Spears, Backstreet Boys, Avril Lavigne. And on the other side, I'm not sure about the others. I know only Eminem, and probably I've heard of Jay-Z. But I can guess that it's probably hip-hop something. So, but you can do such experiments already with your knowledge in programming. So, and yeah, that's pretty much it, what I have for today. And enjoy the weekend. Play a little bit with this texts and lyrics. And I will see you next Friday. We'll have advanced lecture about language models, large language models, etc.